Today's tutorial is all about double integrals. And if you were here for the Monday tutorial, I did this one here. Now I'm going to redo this for this class because, well, first of all, the questions are the same this week. And secondly, I watched the video again. Oh yeah, I watched my own video. And I wasn't real happy. I didn't think I nailed that particular question. And the rest of the tutorial will be on polar coordinates and application. So we'll do some of the harder sort of visualization type problems from section 11.1. Okay? All right, so I'm going to start with 104. So we've got omega, some two-dimensional region, bounded by this line below and above by this circle. Assuming that the density is uniform, calculate the centre of mass of the region omega. Okay, so the first thing we've got to do is draw a picture. These kind of problems, as I'm sure you're becoming aware, they really need good spatial awareness and understanding. So for me, I like to draw a picture first. So let's actually do this. Okay, so we've got a circle and a line basically. So it's the unit circle and it's centered about the origin. And you've got a line, x plus y equals 1, and it actually cuts the axes and intersects with the curve. So this is the curve x squared plus y squared equals 1, the circle, and this is the curve y equals 1 minus x, or x plus y equals 1. So the region of interest then is bounded above by the circle and bounded below by the line. So it's just this little region here. Now, there's a little hint in the question. It says, hint, use symmetry to help calculate the centre of mass. Well, firstly, we realise that our density function, and this is just from the question, say delta, it's just identically equal to a constant here. All right. So you look at this, the density is constant everywhere. Is there any symmetry in this shaded region? Can anyone see any? Yep. So if I draw this line in, this is the line y equals x, you can see that the omega is kind of, I don't know, reflected in that line. There's symmetry in that line. And furthermore, the density is just a constant. So the density is not going to play a huge role in this. So what does that mean? Well, it means that the centre of mass of this little sort of plate has to lie on this line. Okay? So this is the first So due to the symmetry and, I guess, due to delta being equal to a constant,
will it be the midpoint of AB at points A and B at the intersection of?
No, not necessarily. I don't think so. We can find out though. Our centre of mass lies on the line y equals x. Okay, so let's, so what does it mean? I.e. centre of mass satisfies this. So in other words, we only have to find one of the components of our centre of mass point. Then we immediately have the other one. All right, so what's our centre of mass? Well, I'm just going to get the y component first. I don't really know why I did that. And also in Monday's lecture, I wrote a x bar here instead of a y bar. Okay, so even I can get confused sometimes. Right, so this is our y bar point. Now, delta is a constant, so I can take the delta out the front here and cancel. Okay, so I can just cancel, because delta is a constant, right? And now if you look down here, this is just the area of our little region. Okay? Now, is there a quick way to calculate the area? Well, yes, it is. It's just the area of a quarter circle minus the area of this triangle. Okay? So the area of this quarter circle is going to be pi on 4. And the area of this triangle is going to be a half. Okay, so I don't even need to do a double integral for that one. For the bottom anyway. For the top, I am going to have to do some calculations. Now before we get down to the evaluation of this top integral, I have to describe my region, omega, mathematically. So let's do that. Now you could use polar coordinates are probably not a good idea here, but think about this top curve. This top curve, from here I can just rearrange this and make y the subject. The top curve is going to be y equals root 1 minus x squared, right? And this curve here is just y equals 1 minus x. So if I vertical line in, I can see that my vertical line enters my region omega at 1 minus x, and it leaves the region omega at root 1 minus x squared. How far do I have to shift along the x-axis to sort of cover my region omega? Well, I move my vertical line between 0 and 1. So there are the bounds on my region. Okay, so x is going to be between 0 and 1. And y is going to be between 1 minus x and, if I rearrange this and look at this curve here, root 1 minus x squared. Okay, so that's the hard part. All I've got to do now is evaluate this integral with these limits of integration. Okay? So let's see if we can do that. Take a new page. All right, so my limits of integration were x between 0 and 1, y between 1 minus x and root 1 minus x squared. And I'm integrating y. So next one would be dy, because that's where my y bound is. And then the other one would be, of course, dx. So let's do the inside integral first and move on to the outside integral. So in the inside integral, I'm integrating y with respect to y, so I get something like a half y squared. So I can take that half out. When I plug in the square root sign, that's going to disappear. So I'm going to get 1 minus x squared. When I plug in this, I'm going to get 1 minus x. So now I've broken it down to a single integral. So I can just simplify this if I can, and then do my integration. So according to my calcs, this will simplify down to something like this. So I'll get, hang on, I've forgotten the squared sign. Whew. Okay, when I sub that in for y, I'll get all squared. Okay, so according to my calcs, you'll get down to something like this. So the 2's and the half will cancel. And you integrate this, and you'll get 1/6. Okay, so to get our centre of mass, what you want to do is take that and divide it by that. Okay, so we're just applying this little formula here. So our y bar is just 1/6 over pi on 4 minus a half. And if you simplify the algebra there, and we know from symmetry, this is also the x bar. So our conclusion, centre of mass is just now, is it the midpoint? I don't know. That's something to think about. It's a good question. It's a good question. I reckon if it was a rectangular region, it would be for sure. But I'm just not so sure because it's a curved region. It's a good question though. Any questions for that one? So as you can see, setting up your picture is really important. Setting up your picture is really important. Okay. All right. Oh yes. I'm going to do 107B by popular demand. Okay, a few people have been asking about this one. Find the volume lying inside this sphere and the cylinder. Okay, and you've got equations for the sphere and the cylinder. Okay, so let's actually draw this and see what we actually want. All right, we've got, so this is 107B. So we've got the solid inside the sphere. And also inside the cylinder. Oh, inside. So A is just a constant, a positive constant. So the first thing with this one is I would just draw a picture. Okay? You've got some sort of badly drawn sphere. And inside that, you're putting in some sort of cylinder. Okay? And what you want is the volume of the cylinder, right, plus these little end bits. Okay, it's badly drawn, but hopefully you get the idea. So you've got a cylinder with two little round bits on the end of it from the sphere. You want that volume. Okay? So what I'm going to do, I'm going to draw this in the, I'm actually just going to draw the top half of it because it's symmetrical, right? You've got the following. I'm going to draw in a hemisphere. And then inside, I'm going to draw the top half of the cylinder. So what we want here is the volume of this region here. Now, this will cut it something like, so this is just the top half of the cylinder. We'll calculate the volume for that and then we'll double it. Okay. All right. So essentially, what we're doing, we want the volume that lies below this part of the sphere and above this discular region in the xy plane. Okay, now that's the key to this question. You've got to think, okay, I want the volume that lies above this discular region bounded by this cylinder and below this part of the sphere. Okay? So that's the key. All right. So what I have to do then is go, all right, well, this is the sort of the top bounding curve, so that's no worries. What is the equation for this? Well, let's draw that in the xy plane. Okay, this is our region of integration. Well, this is just the circle associated with this in the xy plane. So this would be A, this will be A. This is, again, just x squared plus y squared equals a squared. All right, let's do the actual calculations. So let's call this, I don't know, let's call this S. Oh no, S is a bad word. Let's call this omega. Okay, the whole thing, the solid that we're interested in. Now, the volume of omega is going to be 2 times the volume in here. Let's call this D. Now I know the volume of a solid that's bounded by some surface, Z equals F, say, and that lies above some region D, is just the integral, the double integral of Z by 2, because you want 2 lots of this volume to get this. Okay? Now, I can take my Z from here. So let me just start on another line. And the question is, how can I describe my region of integration D? It looks a bit nasty. Any ideas? Any ideas? How can I describe that region D? Well, I could sort of get the curve for this. This is the y equals positive square root a squared minus x squared negative square root. But that's not going to be very, very nice. So what I suggest is that we switch to polar coordinates. Okay? So we're going to basically change the dr to an rdr d theta, and I'm going to put my limits of integration in with respect to polars. So what is d described in polar coordinates? Anyone want to have a crack at it? So in polars, I know I'm going slightly off the screen there. What's d? So it's r and theta. So who can tell me what's r going to be between for this to trace out this circle here, this disk? 0 and, yep, correct. R is going to be between 0 and a. And what about theta? How much of a turn do I have to do to sweep out the whole region D? That's right. Good. Okay, so let's do it. It's going to be 2. Okay, so it doesn't matter which way you do the integration in this case because it's just a polar rectangle, I guess. But I usually put the theta on the outside just for good measure. Now, you replace x with r cosine theta. You replace y with r sine theta. And you replace r with r d theta. Okay, so it's a bit of a mess now, but we can use cosine squared theta plus sine squared theta to simplify, right? So actually, I'm going to get root 2a squared minus r squared, and you've got another factor of r over there, so I'm going to put that down there. Now, a lot of students forget about the r. Okay, they forget about that factor of r. They just look at this and go, oh, I can't integrate that. So I'm going to bring it over to the front. Now, usually integrating square root signs are a real pain, but in this case, this factor of r helps us out, right? Let me show you. I know that when I integrate, that square root sign's got to go to a 3 on 2. And really, all I've got to do is adjust it somehow by multiplying by some number. Okay, so let's do the inside integral first. So that square root's going to go to something like 3 on 2. So I'm going to write it down like this. And then I'm going to adjust. Now, if I differentiate what I've got here with respect to r, I'm going to get that 3 on 2 is going to come to the front. The minus 2r is going to come to the front. So I'm going to get a minus 3 out the front. But I don't want that. I'm going to get a minus 3r out the front. But I don't want that. So I'm going to counteract that with this minus 1/3. Okay? All right.
Why didn't you eliminate the 2?
The 2 because it's because the 2 already is eliminated with the half up here. Yep. So now if I guess I can take that minus 1/3 out the front. When I sub in, I'm going to get 2a squared minus a squared, which is just going to be a squared to the 3 on 2 minus 2a squared to 3 on 2 d theta. Now, if I look closely, nothing in here has anything to do with theta, so I can just multiply. When I do my integration, I'm just essentially multiplying by 2 pi. I've got a common factor of a cubed, so I can take that out the front, and I'm going to get something like 1 minus 2 root 2. Okay, and if you put the minus, if you want to distribute the minus sign, then it's just this. Okay. But you can see with that kind of question, you really need to draw a picture. Okay, even like the top students in this class are asking about this one in Monday's tutorial. So I'll do one more, but I'll just show you how to do the geometry, like set up the sketch. 108. 108 looks really hard, but it's not hard. You've got some region determined by the following inequalities. Sketch the region and find its area. So I'll just sketch the region. So this is 108. So the inequalities are y is non-negative, y is greater than or equal to minus x squared plus y squared is less than or equal to 3 root x squared plus y squared minus 3x. Okay? Now that looks like a big mess. But remember, we're trying to use polar coordinates to simplify things. Okay? So this is pretty clear. We only want points to the right of the, above the x-axis, right? This is pretty clear. I can draw the line in y equals minus x and satisfy that. But what's going on with this? Well, what I'm going to do is work on this inequality and then...
Could you just switch to polar sheet?
Yeah, you can. Well, I'm going to replace that with r squared. I'm going to replace that with r squared because, you know, just replacing x with r cos theta, y with r sin theta, and you'll get r squared is less than or equal to 3r minus 3r cos theta, and you can just simplify that. Yeah, so let's look at it. So let's call this star, you guessed it. So just the inequality, basically. So I'll replace x with r cos theta, y with r sin theta. On the left-hand side, I'm going to get r squared. On here, I'm going to get 3r minus 3r cosine theta. Now, I've made some assumption there when I've cleaned up the square root sign. I'm assuming that r is non-negative. Yeah. Now, I can furthermore clean up here if, like, just basically by cancelling off the r's. Now, I'm assuming there that r's not equal to 0, which is a reasonable assumption because if r's 0, then it's just trivial, right? You're just at the origin still. So cancel, common factor of 3. I get something like this. Okay, so I'm going to draw r equals 3 bracket 1 minus cosine theta in the theta r plane. And then I'm going to transfer it into the xy plane.
Still r squared, isn't it?
No, I've cancelled one of the r's, yeah. Okay, so if I consider r equals 3 bracket 1 minus cosine theta, then I'll get I sort of get the following. So this is 6, this is 3. So it's basically just these set of points here. So this is r equals 3 bracket 1 minus cosine theta. So now how do I transfer that into the xy plane? Well, I'm glad you asked. Well, when theta equals 0, r equals 0. So I'm starting here. As I move to pi on 2, in other words, a quarter turn, I move up to 3. Then as I go through to a half turn, I move up to 6 units away from the origin. So it'll be something like that. And then I get back to 3 and then back to 0. So it'll look something like that. Feel the love. Now this isn't the whole situation. This is only from this underlined inequality. We've still got to worry about y greater than or equal to 0 and y greater than or equal to minus x. Well, let's draw in the line y equals minus x. It'll be something like that. And I want y greater than or equal to 0, so it's just everything up here. So let's look at that. There's our omega. Okay, so we've got a picture, great, but let's try to describe it using polars. Who thinks they can do it? Well, let's try the easy. Well, how much of a turn do I need? Well, I need halfway between a half turn and a quarter turn, right? So theta is going to be between 0 and 3 pi on 4. Okay? And what about my r? What are the bounds on r? Well, if I draw any sort of vertical line or any line going out here, it enters the region at 0 and it leaves the region at this curve, which is r equals 1 minus, 3 bracket 1 minus cosine theta. There we go. Okay, so that took us a long time to draw all that. What we're trying to do is find the area of this curve, of this region. So remember, the area is just the double integral of 1, of the constant function 1 over the region. Okay, so in this case, I want to move to polars, so I'm still replacing my dA with r dr d theta. And that's going to be my double integral. Okay? Now, so you're going to be integrating r, you'll get a half r squared, substitute in and then integrate again. I'm going to leave you to do that.